Okay, it's a great pleasure for me to introduce the morning keynote speaker, Geoff Zeiss. He's someone who I've been reading his writings for many years. Hail him as a guru when anything to do with underground. When this event was getting planned, one of the first names I thought of for a keynote speaker was Geoff Zeiss. He's a principal at Between the Poles. If you haven't looked into that blog and website, I would suggest you do if you have anything to do with underground. Geoff has authored papers. He's been published in also in XYHT magazine as a regular contributor. And Geoff is going to start off his session with a poll question. Take it away, Geoff.
Great. Good morning, everyone. I hope everybody can hear me and see me this morning. Thanks, Anne, for organizing all this thing, and thanks a million, Gavin, for the introduction. What I'd like to do, I'd like to start off with the poll question here, just so we have some idea of who the audience is. So we'd like to get some idea of whether you're in the construction business, whether you're working for government, whether you work for a utility or a telecom, and also just how important knowing where things are, how important that is to you in your work, not your what you worry about in the evening, but during your day job, what's important to you. So you'll have a couple of minutes to do that. While that's happening, I'll just give you a little bit of an overview of what I'm planning to talk about this morning. We have a fantastic lineup through the rest of the day. I'll touch on a number of the things that will be talked about in much more detail later in the day. So I hope I give a little bit of an introduction to what you can expect from other speakers. But what I'm going to cover is, first I'm going to cover the context for what's happening with respect to underground in the construction industry. The construction industry has labored under a major problem for about 40 or 50 years, and that is productivity, which for many of the world's leading economies has not changed. Construction productivity has not changed for about 40, 50 years. It's plateaued, in some countries even gotten worse. That has resulted in a significant amount of investment in technology and other things. And I'll just touch on that because there is now some evidence showing that since 2018, that has really started to take off. Now, what I'd like to do is share my screen. Okay, as I said, there has been a real problem in construction for a long time. And construction is a $10 trillion a year business worldwide. So it's roughly on the order of 8% of the world's total GDP. And you can look at these charts. These are from a number of different sources, but you can see they deal with Germany, United Kingdom, Japan, EU, South Korea, US. But what they basically show is that while industrial productivity has more than doubled over this period of time, construction productivity has either stagnated or dropped, as you can see from the slide. The United States construction productivity has even dropped. Now, what's happening is there's a lot of private money going into construction now for infrastructure, to pay for all this infrastructure that we need. I won't spend a lot of time on it, but it comes from pension funds, it comes from sovereign wealth funds, and it also comes from insurance companies. There's an estimate, there's something on the order of $60–70 trillion ready to invest in things. And it's only since about 2003, 2004 that money has started to flow into construction. Traditionally, construction has invested very little money in R&D. If you, very interesting study done by McKinsey looking at the degree of digitalization of various industries, something like 27 or 28 different industries. Construction is way down with hunting and agriculture. So it has been traditionally underinvesting in R&D. But as you can see, there has been gradually since in the last 4, 5, 6, 7 years, something like that, there's been gradual investment by venture capitalists into startups and also by well-known companies that are also investing in this area. For example, like at Geosystems. But you can see since 2018, it's more than quadrupled. And this is at the beginning of a trend for a lot more investment in technology in construction. So what we're talking about is not something that's isolated or related solely to underground infrastructure, but there's a general phenomenon of more investment in technology for construction. So I think most people on this call, just from the survey, are aware that not knowing where things are underground is a real problem. It causes construction delays. It's a major cause of delays for highway construction projects. This is a quote right from the Federal Highway Administration. And I'll give you an example of a very innovative project, innovative project from the Alabama DOT. This was a major interchange project in downtown Birmingham, so it was a really busy place. And what they did on this, which is quite different from general practice, is that they spent several $1 million doing this, creating a 3D model of above and below ground utilities. They did GPR scanning, they used existing as-builts, they did potholing, and so, the normal things you would expect for locating things underground. But after the project, they estimated that they saved over $10 million on this thing, and probably most importantly, for a highway project of this magnitude to finish on budget and on schedule is quite remarkable. This is an interesting statistic that I dug up, and that is that if you look at the number of deaths from underground utility data over a period of 20 years, this is from CGA, it's something on the order of over 400 deaths and maybe 2,000 injuries, something like that. So this is hazardous stuff. And I think the interesting comparison is with the U.S. commercial airline crashes. This is from commercial airlines. This does not include Piper Cubs and things like that, but it's roughly the same number of deaths, over 400. This does not include 9/11. The interesting difference is that the budget for the FAA, which regulates and whose objective is to reduce airline incidents, their budget is something on the order of $20 billion annually. If you look at the equivalent, I guess PHMSA might be the equivalent on the underground side. That relates to underground pipelines, mostly gas transmission and hazardous fluid pipelines. Their budget is something on the order of 250 million. So we are obviously devoting a lot of money to reducing airplane crashes, and it has. I mean, if you look historically, since 1929, which is the high point, it has been a process of continually reducing the number of airplane accidents. And I'm sure you're aware just how quickly with the 737 MAX, how quickly after those two incidents, everything was grounded. So there's very detailed processes for managing how planes fly, airports, and so on and so forth. In the U.S., I've estimated that underground infrastructure, not knowing where things are, represents something on the order of $50 to $100 billion drag on the U.S. economy. This is a little difficult to estimate because there's direct costs. That means what the utility company has to pay to fix the problem directly, but there's the indirect costs, and that includes things like traffic disruptions. It includes things like loss of custom, property damage, and environmental impacts, legal issues, and injuries and fatalities. There's some research by the University of Birmingham in the UK that estimates that that it's roughly on the order of 30 times the direct cost, and if you multiply that out times 400 to 800,000 incidents, that's the number from the CGA. It comes out to about $50 to $100 billion drag on the U.S. economy, and I think that's an underestimate when you look at all the implications of hitting underground utilities and telecom. Now, it's interesting to compare the U.S. and Japan. As I said, in the U.S., it's roughly on the order of 400,000 to 800,000. The actual number reported to the CGA in 2016 was something on the order of 390,000, but that's clearly underreporting. For that same year, the number of incidents reported in Japan was 134. And I haven't left off zeros or anything on that. There's obviously something that can be done about this. This is just the way business is, and there's nothing we will be able to do about it. So something can be done. So I'm going to talk a little about some really interesting innovations. I break it down into innovations in detection, and the other one is the other really big area is innovations in sharing, recording and sharing and updating the stored data. So you're probably familiar with a lot of these, but I mean, I think everybody would agree that EM detection, whether you're talking about, there's about 3 or 4 different techniques based on electromagnetic technology, is the most widely. I think the last time I did a survey on this, 75% of the respondents said that they used EM. So EM is widely used. It's inexpensive. It's very good for conductive underground infrastructure. And it can be integrated. And in this particular instance, this is an example from a company called TerraFlow Geomatics. They have been able to integrate an EM wand with RTK or RTK GNSS and digital capture to a handheld device to actually record a digital record of the location of underground infrastructure. So this is a big thing from the point of view of not just painting the ground or sticking flags in the ground, but actually capturing a digital record of what you found. Another really interesting way of capturing what's underground, especially for new infrastructure, is basically putting a LiDAR scanner on the side of a pickup truck and running it down the trench before it's filled. This is something that has been done by Lux Modus. It's very effective for new infrastructure and is being widely used in the pipeline industry. This is another thing. A number of companies now have been able to improve on the speed of capturing radar, ground penetrating radar, to the point where you can run a truck with either with a rig behind it, like with a trailer behind it, or with a rig attached to the truck down a road at 130 kilometers an hour and capture a ground penetrating radar scan. There's a lot of post-processing afterwards to do that. And some systems are actually including not only ground penetrating radar, but above ground LiDAR, so that when you get done with this, you have a record of what's above ground and what's below ground. Another really big problem with ground penetrating radar is interpreting the scans. You can see on the left at the top there's typically a lot of hyperbolas, and this generally requires a geotechnician to make a lot of sense of this. But there has been a really interesting development in basically combining scans and producing a tomographic display with no hyperbolas, which makes it a lot easier for people who are not geotechnicians to interpret these scans. And this is something that surveyors have been particularly interested in. Another technique that a lot of GPR companies now are using, this is not a new technique as being applied, for example, in seismic technology. It's been used there for many years, but that is using statistical averaging. It's called stacking to improve the signal to noise ratio. So that, as you can see in this, this is from Sensors and Software. You can see that the scan is reaching much further down and is showing features with better clarity. Another area that has been used for quite some time, but now is because of the digital capabilities and batteries and so on, is now being able to be used for distances up to 2 kilometers of underground pipe, is inertial mapping. Which can actually generate as-built or other types of information with up to 15 centimeter accuracy in all three dimensions, X, Y, and Z. And the results of that can be exported for AutoCAD or KML, for example. Acoustic surveying is also something that's been around for a while, but it hasn't really been applied in this area. But there's some early results that show this is really pretty effective for certain types of underground infrastructure, and that it can be effective down to 30 feet or 10 meters. And it's not affected by soil conditions, which is something that severely restricts how far you can use GPR. Capturing the location of underground utilities to centimeter accuracy generally has required a surveyor, which means if you expose some infrastructure during construction, or if you have just put some new infrastructure in the ground, you need to have a survey crew on site, or you have to call them to your site to do a traditional survey. And that is used. That is now mandated by several jurisdictions, including Montana, and we're going to hear about that later. But now there is technology that allows you to capture very accurate as-builts by walking along the open trench, or by capturing the exposed infrastructure with a handheld cell phone. It can be a video, it can be a still photo, or whatever. Generally requires either accurately surveyed control points, or GNS, RTK base stations, and so on to get the required level of accuracy. Augmented reality, we're going to hear a lot more about this later. I won't spend a whole bunch of time on this, but it's something that allows you to integrate 3D models, CAD, traditional GIS, and other things. There's another number of companies that are doing this, but allows you to go out in the field and actually visualize what's underground with much greater clarity than you've been able to do with paper maps, for example. We're going to hear more about standards in the future later this afternoon. 3802 has been around since 2002, and there's a new ASCII 3820, which is, I think it's available for public comment now, or will soon be, and we're going to hear more about that this afternoon. In the UK, there's a PAS 128 standard that's used in the UK, but widely other places as well, and that's currently under revision. There's other standards in Canada, Australia, and Singapore, but I think what's really interesting about those two standards is they're being revised to take account of the new technologies for detection that have arrived in the last few years. There's also a standard being developed by the OGC for interoperability. I won't spend a whole bunch of time on this, but if you are interested in it, just look for MUDDI, MUDDI, Standards Working Group, and they are looking for people to participate in that effort. Now, as I mentioned before, the other really interesting area is recording and sharing information. It's estimated, I've heard estimates that the US devotes something in the order of $10 billion a year to locate underground utilities. And often it results in paint on the ground or flags in the ground, but the information is often not recorded and it's not shared. So if you have to dig in the same place a year from now, the same thing's going to happen. 7 utilities will converge in their bands with their magic wands and GPR and whatever, and find out where everything is underground over and over again. This is quite wasteful. And I think a number of jurisdictions in North America and in other places are doing something about this. Colorado, I think it's remarkable what Colorado has done. This was motivated by a disaster in Fremont, I think about 3 or 4 years ago. I won't spend a lot of time on this, but I think it's remarkable what's going on there. And the fact that this data is now being, it can now be shared between Colorado DOT, major and small construction contractors, and network operators. It's accessible by mobile devices in the field. And I think one of the most remarkable things from a data quality point of view is that it enables you to do updates from the field. Field folks can do updates from the field during construction. I also mentioned earlier that Montana has mandated accurate as-built. This means that anything that new goes into the ground has to be surveyed by either a professional engineer or a professional land survey. And the accuracy has to be on the order of a third of a foot. The data is recorded in a system. This is a system developed by GeoWorks, and we're going to hear from GeoWorks later today, and is accessible from a mobile in the field. This doesn't address existing infrastructure, but it means over time, the quality of the data, location data, and other types of data about what's underground is going to improve. The Scottish Vault system is really quite remarkable. It was started in 2012 as a voluntary system for sharing information about the location of underground infrastructure. It involves a collaboration among national, Transport Scotland, local government transport agencies, and over 70 network operators in Scotland. And legislation was just passed last year to make this mandatory. It has been very successful. It's gradually displacing the Scottish one-call system. And I think it is really a model for the world. It was developed, the software for this was actually developed by the University of Leeds and implemented by a company called Simology. I think there's a number of people around the world that are very interested in what's going on here. There's a national underground asset registry being developed in the UK. This is by the Geospatial Commission. 2 pilots have been completed so far. And I think the most remarkable thing about this is that 40 utility and telecom network operators and local government agencies agreed to share their data for these pilots. This effort has resulted in a harmonized data model, so all this data can go into a common data model and be displayed all on the same map. Common symbology, so everybody agrees that what you see on the map, what it represents. It is also interesting, like the Colorado system, the ProStar system in Colorado, that enables feedback from the field. There's something called observations, which allows people out in the field to say, no, this is incorrect. It's the wrong type of equipment. It's in the wrong location. It's off by 5 meters, whatever. As part of the pilots in the UK, a working prototype online system was developed by the Ordnance Survey for sharing location data over the web to handheld devices in the field. And I actually went to the UK and experienced that. The next step on this will be a RFP or a request for people to bid for a national rollout of this system for England and Wales. The Netherlands developed quite a few years ago. Developed a Click, what's called Click, but it's an online one-call system. It is very efficient. You can go onto the system, define a polygon, and within 24 hours you will have a map of everything underground. It also is now mandatory in the Netherlands to report incidents of underground damage, so there are reliable statistics there. But the very interesting thing, and I'll talk about this in some other jurisdictions as well, is that so far the statistics provide no evidence that the system has reduced utility damage during excavation. It has improved construction productivity. It has generated reliable statistics, so you can assess whether new programs have been effective and so on. But to date, just having an efficient system for doing one calls has not shown evidence that it reduces underground damage. One of the really interesting things that's happening in several jurisdictions around the world is open data. This is a goal, as you know, U.S. government, many governments have a goal for transparency, for using open data for transparency, but it remains very uncommon among utility and telecom operators, and in the United States for certain types of critical infrastructure, it's actually illegal. I came across it first in a place called North Shore City, New Zealand in 2008. Australian water companies have made a lot of their data available publicly through open sites. And one of the most remarkable initiatives in North America is by the Colorado Oil and Gas Conservation Commission, which requires the oil and gas industry to provide maps of flow and gathering line infrastructure. This is for often fracking wells. And there's pipes from the fracking wells to pipes and to tanks, and from those tanks to collector stations and pumping stations and so on. And the really interesting thing is that you can go to this site and you can see maps of all the underground flow and gathering lines in Colorado. Again, this was the result of a disaster in Fremont, something like 3 or 4 years ago. But I think this is a remarkable initiative that this is publicly available. As I mentioned, reliable statistics are essential for determining whether you have an effective program for reducing underground infrastructure. CGA collects a lot of data, but again, I think everybody at the CGA recognizes that they're not getting everything. But if they use just what they call consistently reporting sites, the evidence, and they prorate things to the amount of annual construction, the evidence shows that underground damage is not getting better. In other words, it's not being reduced. In Ontario, there's something affiliate of the CGA called the Ontario Regional Common Ground Alliance. They have very good statistics also on things that are going on in Ontario, and they report something called the damage ratio, which is the number of incidents per 1,000 one-call notifications. And you can see that this improved. It improved dramatically from through 2014, but since then it is actually gradually increasing. PHMSA, as I mentioned before, it's mandatory to report pipeline damage to PHMSA. But if you, they've analyzed the statistics and they've prorated it to things called, to what are called high consequence areas. But they have not seen any significant reduction in pipeline incidents as a result of the measures they've taken. HCAs was one of the first things they did. They've just recently introduced something called MCAs, which are medium consequence areas, to try to address reducing pipeline incidents. As I said before, the Click online system in the Netherlands has definitely improved construction efficiency. It's gathering statistics, but it has not reduced utility damage. The one example where things have improved, there's actually two. There's Japan and Heathrow that I know of. I'm sure there's others, but those are the two I know of. I don't have time to spend on Japan, but they started in 1985, and since then they have reduced, as you saw, they have reduced their number of incidents dramatically to 134 in 2016. At Heathrow Airport, the statistics show that there has been a continuous reduction in underground network damage. You can see that the green represents the number of requests for excavation permits, which are the measure of construction activity at Heathrow, and the yellow measures the number of strikes the percentage of strikes per permit, and you can see that it has been consistently going down since they started recording this around 2001, 2002. So those are two examples, and I think that the takeaway from those is that there is really no silver bullet for solving this problem. Having an efficient online one-call system like in Netherlands, Click, there's no evidence that by itself does it. Probably, I would guess, probably because the information, the as-built information that they're getting from the utility operators is probably not at the quality that it should be. There may be other reasons as well. These are some of the elements that were identified at Heathrow. They have a very complex 7-step process from preliminary design to handover for excavations at Heathrow. And it involves accurate reporting of what was put in the ground, other things that were found during excavation, and so on. You cannot excavate within a certain distance of a utility except using hand digging or vacuum or hydraulic extraction. That's based on the PAS 128 quality levels. You have to report any underground services strike, which I think at an airport, I think that is obviously, that is an obvious requirement. And the other thing that's really interesting about Heathrow is that people involved in detecting and mapping underground infrastructure have to be trained and certified. You can't just hire somebody off the street, give them a GPR and say, go out and find things, or give them an EM device and say, go out and find things. Those are just a few. I've written a white paper recently together with a colleague of mine, Professor Shinoaki in Japan, which identified 25 elements that can contribute to reducing damage to underground infrastructure. And I think that from the point of view of innovations, these are probably the most important ones, and these are the things we're going to hear a lot about today. And advances in detection technology, efficient survey grade capture of new infrastructure in the ground, legislation, for example, in Colorado, that requires a subsurface utility engineering survey prior to engineering design, not just prior to construction, but prior to engineering design, so you can design things that avoid utilities, which avoids unnecessary relocation of utilities. We're going to hear a lot about the next one, technology for recording, sharing the location of underground utilities, rather than just throwing away $10 billion worth of effort every year. I mentioned open data, which I think is something that is beginning to happen in several jurisdictions around the world. Access from the field on mobile devices seems to be a real requirement of any of these new technologies for sharing information. And I've mentioned two jurisdictions that are already enabling updates from the field. The newer initiative in the UK, the National Underground Asset Registry in the UK, pilots, and I expect that will be a requirement when the RFP comes for that project over the next year or so, something like that. But also the Colorado DOT solution also enables updates from the field during construction. And I think those are some of the key ones. But as I said, we've just published a white paper that has 25 things that can contribute to improving data quality. And I think there are, as I said, there's two examples, Heathrow and Japan, where these have actually been implemented and have been shown to work. So I hope that was informative, and I thank you for your attention.
Thank you, Geoff. We're going to jump right into the questions because quite a few have popped up already. I also wanted to thank you for the paper that you and Dr. Shinoaki had put together and allowing a summary of that to be published in the July issue of XYHT. The folks can find that at xyht.com. So jumping right into the questions from the users, you mentioned Colorado, Montana, Netherlands, Scotland, these systems. What's the source of the location data that's going into those? Because that probably varies a bit.
It does. It's very interesting. I mean, you can look at, like in Scotland, for example, it comes from the network operators. Okay. So it's coming from the utility companies, it's coming from the telecom. And that is a challenge because, telecom, for example, is very competitive. And telecom operators, if there's any possibility that their network diagram showing where all their fibers are in particular would be accessible to a competitor, that would be a showstopper. That's why data protection is a really big thing. I didn't spend a lot of time on that this morning, but data protection is really critical because you have to have restrictions. For example, in some jurisdictions, there are restrictions that when you define your polygon, it can't exceed 500 by 500 meters, for example. You can't go in and say and do 10,000 requests at a single sitting, for example. And that's basically data protection mechanism. Other jurisdictions in Montana, and I'm sure the Montana folks Montana DOT folks can talk about this. But Montana, to date, from what I understand, it is only new infrastructure that is being captured into that system.
Oh, okay.
So, and that requires, as I said, it requires either that has to be stamped, signed off by a professional engineer or a PLS, professional land surveyor. So that
Geoff and Gavin, this is Eric Berkowitz. If I could,
yeah, Eric, yeah, go ahead.
The system they've installed does and can capture and deal with structures that are already in the ground. So they do have a SU module on this as well. So
okay, great.
And MDT does push SU on many of their projects as well.
Good. Okay, Eric, thanks a million for that correction. I knew your system was capable of ingesting SU data. I just didn't know whether it happened yet. And if you look at other systems, sometimes it's only data that is currently being accessed. In other words, it's only data, for example, when utilities are exposed during excavation, that data may be captured and stored. Because they haven't worked, one of the real challenges is working out data sharing agreements with utility companies and especially with telecoms. And that's what I think is so remarkable about Scotland and the National Underground Asset Registry in the UK is making it, the fact that they have managed to get 40, I think in the case of Newer, 70 in the case of Scotland, utilities and telecoms to sign data sharing agreements to share their data.
Okay, yeah, I reviewed data from a utilities mapping initiative in the Flanders part of Belgium years ago, where it was mandated, but they also got everyone to agree on it, and they went in on a real-time network to help with the mapping. But that's, it's hard to do on a much larger scale. A quick question from Michael T. What are the obstacles to creating, and you've been covering this, answering this already, to creating public underground infrastructure registries in North America in particular? If publishing location saves lives, why isn't a registry required?
Well, that's interesting. I was at Arizona State University about maybe 2 years ago, where there were a number of organizations in the US who had proposed that there should be a national infrastructure map. This would be pretty close to what UK is trying to do, what the Geospatial Commission in the UK is trying to do with the National Underground Asset Registry. In the Netherlands, there's something called, it's called BRO, B-R-O, but it's basically a registry of underground geotechnics, which means that every time you dig a borehole, you have to report that information to a central registry so that anybody digging in that same area would have access to what you did. As I mentioned, in the United States, there's something called critical infrastructure protection. This was passed shortly after 9/11, I think maybe a year or two after 9/11, and it restricts, it's voluntary. It doesn't require every utility and telecom to participate, but it restricts access to some underground infrastructure. And I won't go into the details of what the actual requirements are, but I think there are some places where open access is there are legal issues relating to open access to underground infrastructure. So as I said, Australia, a number of big water companies, Gold Coast, have, for example, in UK, in Australia, have made their underground water. You can go; they're publicly available. You can go in there and see where the underground water infrastructure is. So I think it's something that's happening. I think it's starting to happen. The technology is certainly there to enable it to happen. I think some of the systems, for example, the ProStar system at Colorado, the GeoWorks system at Montana, the Simology system that's used at Scotland, whatever system is ultimately used in the UK. I mean, those systems show that this is entirely possible.
Okay. And a question about Japan. So from Randy S. said, why are the number of underground issues in Japan so much lower? Do they require some kind of, SUE or as-built requirements, or do they not record the issues? And well, I did a brief work study at a city engineering office in Japan, and no, it's not that they don't report them. When there's a strike in Japan, especially in some of the very built-up areas, no, there's no hiding that. But Geoff, you worked with Dr. Shinoaki on this. What's the secret sauce in Japan on this?
Well, like I said, the white paper that Dr. Shinoaki and I published, we have a list of 25 things, a lot of which Japan does. I would, if I were going to highlight something, I'd say number one, a construction culture that routinely generates as-built accurate to plus or minus 10 or 20 centimeters. I mean, if I were going to pick one thing off the top, is quality as-built. Right? This is a huge problem. The other thing is, of course, and this was implemented at Heathrow, is construction contractors have to go. There has to be a process for excavation. You can't just say, okay, here's the map, bring out your backhoe and start digging. There has to be, and I think one of the really interesting technologies, which I didn't mention, is using geofencing to prevent heavy equipment from digging within 3 meters, which is what Heathrow says, 3 meters of underground infrastructure. But that assumes that you've got accurate maps of underground infrastructure. So that's why I think the really key thing is accurate as-built. If you don't know where things are and you can only guess, I think it really restricts what technology solutions you can use for preventing underground assets damage.
Cool. I was really impressed with the as-built surveying in Japan. It was ubiquitous. I mean, and it's just part of the project. It's a given, not questioned. Yeah. It's not like, well, okay, we built it. Let's go to the next one.
Yeah,
So,
I would say it's probably a procurement problem in North America. I knew a telecom, I worked with a telecom company in Brazil. They would not pay their contractors until the as-built were in the GIS and verified. In other words, they wouldn't verify every one of them, but they would routinely send out inspectors during construction to verify the location of things. And the contractors that worked for this telecom company would not be paid until those as-built had been verified. In North America, I would suspect that most of the time you get paid as soon as you get it in the ground.
that's true. And where I have seen as-built requirements initiatives, someone will start pushing it in jurisdiction. Sometimes it goes a little far. There's sort of a fit for purpose level, which is affordable. I was impressed, the city of Boston have surveyors specifically that will go out and hit very key points on something when it's been constructed and add that. But I better get to the questions from the users. Ryan W. asked a little bit more information about what is inertial mapping. I mean, I've seen, where the devices that you can run down a pipe that have IMU in it, and it's mapping as it goes. Can you give us some examples?
Yeah, that company that I mentioned is a company, I think it's called Redux. It's a Belgian company, but I know there's other companies that do it as well. They have different size, pigs, or whatever you want to call those little devices that run down the pipe. I think the important thing about these Redux devices is they've got batteries and memory on them, right? So they don't have to be connected to a cable. You can take this little device. There's small ones, there's huge ones. You can take these devices, you can run them down a pipe. And you don't have to have a cable trailing behind them. That's why you can get up to 2 kilometers. And I think that is probably the really big breakthrough, is the fact, besides the IMU, that they have batteries and memory on board.
Okay. Question from Scott C. He touched on that you brought up already about the security issues. You've got carriers that are very reluctant to share their data. I mean, this goes with the public sector as well. I remember after 9/11, there was red zone, they called in public records, in particularly power distribution, that, the records just couldn't be added to a public set.
Yeah.
But that's the security issues question. So Ryan L. said one problem that they've identified is the lack of certifications in education and in designation of underground utilities. I know it's a bit more formal in some other countries. Like you said, in the UK, you've got to be certified specifically in that. Where are we at on an SUE certification that jurisdictions could require?
Well, that's an interesting question. My understanding is, and I'm sure Rob in Colorado or Paige can probably provide better information on that, but I thought an SUE survey prior to design had to be stamped and signed by a professional engineer. Okay. Now, I mean, that I guess you might want to say, well, not every professional engineer. I mean, maybe he's mechanical or maybe he's electrical, and that maybe he needs some additional qualifications in things like interpreting ground penetrating radar or something like that. But I think, as I said, I'm sure Paige and Rob can provide more information on what the requirements are for who does the SUE survey in Colorado.